Our second shuffle for today is shuffle 38, top row on the right. This is also a judicious Klondike, but the stacking here is slightly different. So let's go ahead and derive the permutation for this shuffle. So we begin with our ordered packet 1 through 8, and we'll perform the shuffle and see what new ordering results. So judicious Klondike, this is where you take the top and bottom cards off as 1 into pile 1, the top and bottom card off as 1 into pile 2, top and bottom off as 1 into pile 3, and then the last 2 will constitute pile 4. The stacking is as follows. Pile 1 leaps over pile 2 and gets stacked on top of pile 3. Pile 2 leaps over pile 3 and gets stacked on top of pile 4. And now this time we're stacking the right pile on top of the left. So let's see what the new ordering of the packet comes out to be. So we see that the new ordering is 2, 7, 4, 5, 1, 8, 3, 6. Writing this in Cauchy's 2-line notation, we obtain the following. The top row is always 1 through 8, and the bottom row is 2, 7, 4, 5, 1, 8, 3, 6. We can convert this to cycle notation as follows. 1 goes to 2, so we have an arrow from 1 to 2. 2 goes to 7, so we have an arrow from 2 to 7. 7 goes to 3, an arrow from 7 to 3. 3 goes to 4, so we have an arrow from 3 to 4. 4 goes to 5, there we go. And then 5 goes to 1, which cycles around, completing a large 6 cycle. And then taking a look at the remaining values, 6 goes to 8, so we have an arrow from 6 to 8, and then 8 returns back to 6, completing a 2 cycle, which is also called a transposition. Color coding our digits, we obtain the following. Recall that in the study of Bessey sequences, position values 1, 4, 6, 7 are color-coded black, and position values 2, 3, 5, 8 are color-coded red. This will help us see what is happening to the Bessey structure once a given shuffle has been performed. And once again, there's just 2 possibilities. Either we get the exact Bessey sequence form back, or we get an inversion of it, which is actually the case for shuffle 38, as we'll see. So this means that black 1 goes to red 2, which goes to black 7, which goes to red 3, which goes to black 4, which goes to red 5, and that wraps around to black 1. Black 6 goes to red 8, and red 8 wraps around to black 6. So we see that each value gets sent to a value of the opposite color. And so when that happens, we say inversion has occurred. So again, what this means then is the cards that originally began in positions 1, 4, 6, 7 move to positions 2, 3, 5, 8, and vice versa. And we indicate an inversion by this description here. Using our Bessey sequence 1001, 0110, we can demonstrate that inversion does indeed occur if we apply this particular shuffle. So let's go ahead and perform the judicious Klondike, in which we follow the stacking as listed. So top and bottom constitute pile 1. The top and bottom go off as a single pair. There we go, pile 2. The next top and bottom cards become pile 3. The last 2 cards become pile 4. And the stacking is pile 1 on top of pile 3, pile 2 on top of pile 4, and then we stack the right pile on top of the left. So, did inversion of the sequence occur? Well, it appears that it has. we now obtain the other Bessey sequence of order 8, namely 0, 1, 1, 0, 1, 0, 0, 1. And I do want to point out that every single card has been moved to a different location. And that's because we don't have any fixed points, as we can see here. Every single card is moving somewhere different. But nonetheless, the zeros and ones switch places as a group. And when that happens, we say inversion has occurred. Taking a look at the Bessey shuffle diagram, top row on the right, we see that the transposition 6-8 means that there will be a double arrow between 6 and 8, which there is. And then if we start at position 1, we'll see that 1 goes to 2, which goes to 7, which goes to 3, which goes to 4, which goes to 5, which should return back to 1. So let's check that. So here is 1, 1 goes to 2, so there's an arrow from 1 to 2. 2 goes to 7, there we go. 7 comes down here to 3, so there's an arrow from 7 to 3. Also 3 goes to 4 with an arrow. 4 goes to 5, there you go. And then 5 returns back up to 1, completing this 6th cycle. So regarding the order of this shuffle, we see that it has order 6, which means that this shuffle would have to be performed 6 times to reset a packet to its original order. And as before, I have this tiny little graphic describing a very special feature of this particular shuffle. Namely, in the study of cyclic and mirrored structures, this particular shuffle converts each of our 3 primary types into another in a circular fashion. So 2 cycles are converted to mirrored structures, which are converted to AMP structures, which are converted back to 2 cycles. And this is true for all packets of size 4n, for any natural number n. So this will mean something to those who have studied these 3 primary structure types on the Hidden Structures channel.